Good morning, everyone. We are very pleased, excited, and relieved to present to you our senior project. I'm going to start off by introducing our team. We are Poly Consulting. We're going to introduce ourselves to you and give you a little bit of background on who we are. I am Daniel David, the project manager, and also civil engineer for the civil engineering team.
My name is Brian Tracy, and I am the civil team lead.
My name is Eddie Vega, and I'm the structural lead.
My name is Joseph Escada. I'm a structural engineer on the structural team.
My name is Zachary Draghi, and I'm the geotechnical lead.
My name is Esteban Villanueva, and I'm on the geotechnical team.
My name is Gonzalo Ranquez, the environmental lead.
My name is Shai Zhang, and I'm an environmental engineer on the environmental team.
All right, so to introduce our project to you, we are doing a grade separation project, which grade separations are projects that separate at-grade crossings to address one key issue of congestion and reduce traffic delays. And our project, we're going to separate the railroad from the vehicular traffic. Grade separations are very unique in nature from other projects, as we incorporate all disciplines of civil engineering within it. So with our team, we broke it up into 4 different interdisciplinary teams. First, we have the civil team. Then we have the structures team, water resources and environmental, and the geotechnical team. So each one of these teams are very imperative to complete the design of our grade separation. We like to see it as it being kind of a 4-spoke wheel. Without one spoke, the wheel will not be able to function properly. And that is the same concept that applies to our grade separation project. Without one discipline within our project, it won't be able to be completed. So what we'll do throughout our presentation is show you how each discipline contributed to the final design of our grade separation. First, we're going to start with our project location and take you on a fly through into our site. We're going to start here at Cal Poly Pomona and head on the Interstate 10 East, about 10 to 15 minutes. And we're going to get to a city called Montclair, which is between the cities of Pomona and Ontario. We're going to go south. It's in the southern region of the city of Montclair. And we're going to go to the intersection of Mission Boulevard and head north. As we travel north up Monte Vista Avenue, on your right you'll see a white building, which is an existing fire station. That is a key constraint to our civil team as we went through our grade separation alternatives. We then venture on to the intersection of State Street and Monte Vista, which is also a key objective to remain connected to Monte Vista. Then we'll, just north of State Street, we have the storm drain channel. And then just north of that storm drain channel, we have the at-grade crossing, which we will be separated. We'll continue north until we hit Hope Boulevard. So, as I said, grade separations address a key issue of congestion. Hope Boulevard dumps about 472 vehicles per hour during peak hour flows onto Monte Vista Avenue. Mission Boulevard is another major arterial street that dumps about 682 vehicles per hour at peak hour times. On top of that, we have the Union Pacific Railroad, which has about 192 trains that cross in the middle of Monte Vista Avenue per day. So this yields for a huge amount of congestion in this area, as you see here. So we then identified the objectives of completing the project. We had to reduce traffic delays and congestion. Obviously, we had to see if we can put a signal within our project and minimize the environmental impacts. We also have to protect the storm drain just north of State Street and remain connected between Monte Vista Avenue and the existing State Street. So now I'll pass it on to Gonzalo, who will discuss the environmental analysis.
Thank you, Daniel. All right, as you guys know, every project needs an environmental analysis. This is the case. Now, as Daniel mentioned earlier, we have different types of physical constraints such as the railroad, the storm channel, and of course, the fire station. Now, this was required in order for us to do an environmental analysis. Now, let me explain to you the process of the environmental. Of course, we start with the NEPA, which is the National Environmental Policy Act. Every project needs to follow their guidelines. However, the project is funded by the state of California. Therefore, California itself has their own environmental guidelines that actually the city of Montclair will actually follow and take charge of it. Now, starting from the city of Montclair, the first step for environmental analysis is actually located in the Coastal Environmental Handbook, and it's actually called the Preliminary Environmental Study, or in other words, a PES form. Let me tell you a little bit about this form. It's pretty much divided into 3 sections: the environmental effects and technical studies, the coordination and approvals, and environmental document classification. The environmental effects such as air quality, traffic, noise, hazardous materials were studied and analyzed. And it needs to be coordinated and approved by Caltrans and Los Angeles Regional Water Control Board. And in conclusion of this form, after it was filled out, we concluded that the project was excluded from NEPA. Therefore, the whole project itself did not have any huge environmental impacts. There just needs to be an assessment done. And I'm going to give this to Brian, that will go over the alternatives.
Well, we were tasked with creating a grade separation, not with building any one bridge or underpass. So we need to evaluate our alternatives and determine which would be the best way to complete this grade separation. Is it going to be a railroad trench, railroad flyover, a road underpass, or a road overhead? We will first start with the railroad. This is the existing conditions. We see we have a at-grade crossing between the railroad and Monte Vista Avenue, and this creates lots of congestion and safety hazards that the city of Montclair wants remedied. First option we're going to look at is the railroad trench. We can build a trench underneath the existing Monte Vista Avenue, but this trench will extend for nearly a mile in each direction and be very costly to construct. Our next option is the railroad flyover, and similar to the railroad trench, it will extend for nearly a mile in each direction, and it will affect the grade separations at Central and Ramona Avenue. And this would also be very expensive to construct and not a very feasible option. The next option we can take a look at is the roadway underpass. We can tunnel underneath the railroad and lower the Monte Vista grade. Now this option would require 2 railroad bridges, one for the north line and one for the south line of the UPR railroad line. And it will also affect many underground utilities. So it's not as an attractive an option as our next option, which is the roadway overhead. This option is simply to build a road bridge over the existing railroad, and this option only requires a single bridge, and it affects fewer utilities than the roadway underpass, and it minimizes our impact to utilities. Now here's the vertical alignment that we have for our new Monte Vista grade. The important constraints are we must maintain a 22.5-foot vertical clearance over the railroad at all times and a 16-foot vertical clearance over State Street. When we combine this with our requirements to meet the existing grade at Holt on the north and the fire station on the south, we end up with a very steep exit grade of nearly 7%. In order to have such a steep exit grade of greater than 5%, we need to either have meandering or landing sidewalks. And meandering sidewalks work for our location the best. Now on to the evaluated State Street alternatives. We must maintain connectivity between State Street and Monte Vista as per the Montclair City requests. So, first option is to just close State Street, and that's not going to maintain connectivity, so we can't do that. The next option we took a look at was to raise the State Street Avenue to the new Monte Vista grade. And this choice would require a lot of fill and a lot of retaining walls, and would be more expensive than simply relocating State Street to the south. We take a look at that alternative, we can just close State Street and relocate to the south. Now with this alternative, we still have an at-grade intersection between the new State Street alignment and Monte Vista. And this would create more traffic than having a single connector and just extending the Monte Vista Bridge over the State Street, which is our next alternative. With this alternative, we have the State Street going underneath the Monte Vista Bridge, so the State Street through lanes are not impacted by an at-grade separation with Monte Vista, which greatly improves traffic flow. Now, our traffic analysis showed that we don't need a connector on both sides. We can have a connector on a single side, and we still have adequate traffic flow. Now, after careful evaluation, we found that the west side was less developed and therefore cheaper to construct than the east side. And it also had the added advantage of directly connecting to the fire station, so emergency personnel have direct access to State Street, as they did before this grade separation was undertaken. And now on to Daniel.
So with the connection of, the new connection of State Street to Monte Vista, we implemented 2 new traffic signals. But first I will take you show you what our existing conditions have. Going east to west on State Street, we have 2 unsignalized stops. And going north to south on Monte Vista, we have free flow traffic. This yields over 80 seconds of delay, which also yields a level of service of F. Level of service grades our traffic flow from rating from A to F, F being the worst. What we propose to do is put 2 actuated, uncoordinated signals on the intersections of State Street and the State Street connector, and the intersection of Monte Vista and the State Street connector. For the Monte Vista and the State Street connector, we were able to bring down the delays at this area to 28 seconds, yielding a level of service of C. And for the State Street and the State Street connector intersection, we were able to bring it down to 16 seconds, which yielded a level of service of B. So now I'll hand it over to Eddie, who will talk about the overhead bridge structure.
Thank you, Daniel. As the civil team mentioned, the civil team identified that we would be using an overhead structure. With that, the next step for the structural team to do is to identify which bridge type we would be using for this structure. With that, we identified several bridge types, and when it came down to it, the main types that we considered used different combinations of beam girders, box girders, and different combinations of steel and concrete. Once we identified our different alternatives, we then just defined our criteria. We considered cost and aesthetics, which are pretty self-explanatory, construction requirements, which includes the false work for the different types, as that proved to be one of our most relevant constraints in our design. And we also considered the suitability to geometrical and physical conditions, which includes whether the proposed bridge alternative would be able to meet the span lengths that we were expecting and the design loads that we were projecting. With this, we performed a qualitative analysis using our evaluation matrices. To show you one of these, the evaluation matrices consists of our alternatives and our criteria, each with a different weight value, and we evaluated our alternatives by assigning a poor, neutral, or good rating for each of them, and using the factors to determine its score. With that, when we did our first analysis, we came to realize that we would be most likely using a composite bridge, a pre-stressed concrete bridge, and either a beam girder or a box girder. We came to realize that our ability to design the bridge type would be one of our governing criteria, and so when we add this into our design matrix, it helped us focus in and ultimately decide that we'd be using a composite steel girder with a reinforced concrete deck. And what this bridge type has is a steel girder with the top flange studded to the concrete deck, as shown in the figure. The main rationale for this decision was that this bridge type met the geometrical and physical needs for the project, and also had the additional benefit of requiring less false work, which created less of an impact on the railroad clearance. For our design methodology, we took our approach from top to bottom, where we started with our design of our deck and girders, followed by the design of our bent cap, then with our bent columns underneath, and ultimately concluded our design with our pile caps. The actual pile design was taken by their geotech team. For our seismic design, we performed a pseudo-seismic analysis in which we calculated the period for our structure and then used that period with the response spectra as determined by the geotech team for our site to determine which lateral loads we would need to design for. Also, for the standards that we used in our design, we used our Caltrans Bridge Design Manual and our Caltrans Highway Design Manual. To talk a bit about our span configuration and structural system, we are using a 3-span bridge with simple spans. We initially planned on doing equal span lengths, but we came to realize that some of our constraints made this a different situation. Some of our relevant constraints were the clearance requirements, as that affected our alternative selection. We also had to consider the railroad right-of-way as we tried to minimize our effects of intruding onto that right-of-way. Another relevant constraint was the existing utilities, and as you can see with bent 3, it was located near a fiber optic line, as indicated by the yellow, and a petroleum line. What we ended up doing was moving this bent 3, south, so that we would avoid the interference with these 2 utilities. Another existing or irrelevant constraint was the existing channel, as we had to make sure that the effects of our bent wouldn't hinder the design of the channel, as the channel was not designed for the extra loading from that bend, and that will be talked further by the geotech team. With that, I want to pass it to our Joseph Esqueda, who will talk about our completed design.
Hello, our final design for the bridge is 279 feet long and 79 feet wide. It has a reinforced concrete deck that is 9 inches thick and has a 2% crown. The deck is supported by 9 6-foot deep welded plate girders. The girders are spaced 9 feet center to center. They're connected to the deck through shear studs. Supporting the girders are a bent cap at each bend. The bent caps are 7 feet by 7 feet by 79 feet long. They are supported by 3 5-foot diameter columns, and those are supported each by a 7-foot cubed pile cap. Here we have an elevation of our bridge. It has 3 spans, 2 abutments at each property line, and 2 bends. The first span is 72 feet, the second span is 83 feet, and the third span is 122 feet. Both bents had to have considerations to reduce the impact on existing utilities and above-ground structures. Bent number 2 still had interference with a channel and a fiber optic line, which will be spoken about on the geotech considerations. I'll give it to you, Zach, leader of the geotech team.
Thank you, Joseph. I'll be talking about the geotechnical design and how the various parameters from the other teams impacted the geotechnical design. Just to give you a brief background in the geotechnical scope, we first began with our site investigation background to locate the subsurface conditions. We also, as Eddie had talked about, performed the design response spectrum for earthquake analysis. We also had to design the retaining walls to support the roadway approach and design the foundation system for the bridge structure. Just to give you a brief background into the site conditions, it's mainly a silty sand with a unit weight of 120 pounds per cubic foot and a friction angle of 34 degrees. No groundwater table is encountered at the site, and the historic height is greater than 100 feet, which is good. As you can see by the soil profile, it's varying layers of sand and silty sand with a silt layer approximately 50 feet deep. Okay, so to select the proper retaining wall to use for our site, we took a look at these different retaining walls here. You can see concrete crib wall, sheet pile wall, soil nail wall, mechanically stabilized earth wall, concrete cast in place cantilever wall, and masonry cantilever wall. And so the evaluation that we used for this to select our retaining wall was the following. So the economic wall height, which includes an element of both cost and loading, which is basically taking a look at these walls and seeing what is the expected wall height for these different types of walls. Ours is 33 feet, needs to support a wall height of 33 feet. Second was environmental effects. Is there any impacts from the equipment being used or the wall themselves? The third is aesthetics, which is self-explanatory. Fourth is cost, as compared to one another, which wall is more expensive? And of course, the suitability for fill application. This is perhaps the most important driving factor in our design because, as Brian had mentioned in his civil section, we are having a roadway overhead, so our wall needs to support the structure that is built from the grade up. So here is our evaluation matrix, just as structures had done for their bridge selection. And you can see right off the bat, the first 4 walls you see there on the left, crib wall, sheet pile wall, soldier nail, and soil nailing, can be eliminated because they're not suitable for fill application, which is an important revelation that we made. So those are eliminated right off the bat, leaving us with concrete cantilever, masonry cantilever, and MSE wall. We were able to eliminate masonry cantilevers because they're not really economical at wall heights over 10 feet. So that left concrete cantilever and MSE wall. We chose MSE wall because MSE walls tend to be more cost effective than their concrete cantilever counterparts and are widely used in transportation projects. So the retaining wall design procedure, we used Caltrans bridge design specifications for the various factors of safety required for the geotechnical and internal stability. You can see here on the left the profile of our selected MSE wall design. We're using reinforcing steel strips located within the backfill, which is a form of inextensible reinforcement. The reason for that is to limit deformation in the case of an earthquake. And this is our design, and it was designed for traffic loading, earthquake loading, and of course the weight of the backfill material itself. Now I'm going to hand it over to Esteban, who's going to talk about the foundation system.
Thank you, Zachary. So the foundation system is primarily there to support the superstructure. So the different foundation systems that we considered were shallow foundations, deep-driven piles, CIDH piles, and auger cast displacement piles. The criteria that we used to evaluate these different considerations were the expected loading, which is basically what we expected the load would be from the superstructure, the constructability, any environmental impact in its construction or use, and cost, which is basically, all things being equal, the comparative cost between the different foundation types. As you can see here, this is another matrix which represents our evaluation process. On the top there, you see the different criteria, and on the left, going downward, you see the different foundation types that we considered. So right off the bat, shallow foundations received a very low score. Basically because in order to construct a shallow foundation that would be suitable to support our superstructure, it would be massive and unfeasible. CIDH piles and auger cast piles received the same score, so all things being equal for those, we decided to go with CIDH piles because of their wide applicability in Caltrans projects, and we felt that they would be representative for our project here. And one last note, deep-driven piles received a low score, simply because the environmental impact of bringing a pile-driving hammer to the site would affect all the surrounding locations in terms of pollution and noise. So you can see here, this is the CIDH pile design. We also included the depths for the bent foundations and the depths for the abutment foundations, and also the capacities for each. This is a foundation plan which shows the group effect, basically, of the different foundations in the pile. So you can see per pile cap for each bend, there's 6, and for each abutment foundation, there's 20. So we utilize the group effect to increase the capacity laterally and also vertically for the different pile, for the different foundation arrangements. And here's a close-up. So as you can see, there's 20 there, and 6 each per pile cap. So now I'm going to take you and explain one of the problems or one of the major obstacles that the geotech team encountered. So we're going to go back to the main location here and a closer look. Basically what happened was a pile cap is located just north of a channel that runs through our site. As you can see here, there's a 5-foot clearance between that pile cap and the channel itself. So I'm going to take you on a cross-sectional view of that. So looking at this cross-section, you can see that the shafts are actually transmitting their load to the surrounding soil. However, there is a channel that's directly in the path of that load, which presents a problem. The channel was not constructed to take loading laterally like that. So our selected solution was to deepen the column itself along with the pile cap by 10 feet, which puts the shaft's transmission of loading outside of that column's range. And also, one problem that we get with this is that this column being extended into the soil now has a tendency to act like a shaft itself. So what we could do to mitigate that or reduce that that lateral loading onto the soil was to apply a column isolator, which basically minimizes it or reduces it down to negligible loading. So moving on, I'm going to hand it to Shayu. She's going to talk about the underground utilities.
As mentioned previously by Eddie and the structural team and the geotech team, there were underground utilities that controlled a lot of our design. For example, there's a 16-inch petroleum line running horizontal to the UPRR railroad and the 10-inch sewer line running down Monte Vista Avenue. Also, we had to account for the giant 60-inch storm RCP running down the middle of Monte Vista Avenue as well, and the fiber optic cables running parallel to the railroad. The main utility issues that we came across was that the existing 60-inch RCP was in conflict with the foundation design, as well as the 10-inch sewer. Our solution was to relocate the sanitary sewer, over to the east right of way, and for our storm drain.
All right, so we're going to talk a little bit about the storm drainage design. So these are pretty much the existing conditions right now. I'm going to show you 3 areas that are the main important points that actually drove our design. Let me show you the first one right here in the middle. We have a 72-inch RCP coming down into Brook Street that actually does not connect to this existing 60-inch RCP coming down in Monte Vista. We got 2 catch basins connecting there. So that's something to keep in mind. The other 2 key points is that actually this 72-inch RCP actually deposits water into this detention basin in Brooks. And the channel itself has an outlet that actually deposits water also into this Brooks detention basin. So we're going to run into 3 alternatives based on these 3 important points that I just mentioned. The first alternative actually is to close those catch basins and to shift the 60-inch RCP to the same right of way where the sewers actually is going to be located for the same reasons. However, the issue for this alternative actually is the construction and the cost, because actually this 60-inch RCP will have to be jacked underneath the railroad and connected to the channel at this point. Second alternative that we looked at is actually we're going to create a small detention basin for this 60-inch RCP. However, this is a completely new design, and we're talking about a huge difference, a huge cost elevation for the project on this alternative. And last but not least, alternative 3, which is actually a very interesting one, and the one that actually we take from this, is to connect the 16-inch RCP into the 72-inch RCP. However, for us to do this, we needed to approach this, our design. In order for us to do this, Shayu is going to talk about it, how we approach the design.
So we followed all standards and codes, and we used the storm drain design manual from the LA County Flood Control District. We studied the hydrology and the hydraulics of our project site, and we used computer software to make sure that the water surface elevation remained below grade. As you can see here, we used a rational method to solve for the runoff off of the surrounding site that affected our main pipe of interest. You can see from this graph that our water surface elevation along the entire way from Monte Vista Avenue to Holt Avenue remains below the grade, meaning that if a pipe bursts, the water will not spill spill out onto the road.
So now we'll talk about how we're going to construct our actual grade separation. We broke it up into 2 phases. For phase 1, what we're going to start off with is paving the actual State Street connector. We're going to do that right here. Then next what we're going to do is join the existing 72-inch with the existing 60-inch RCP mentioned by Gonzalo, and also provide or implement a permanent dead-end on Brook Street and give access to the residents in this area by constructing an access road. For phase 2, we already have our State Street connector road paved. So what we'll do is we'll block off Monte Vista and construct our overhead structure, and then implement the 2 traffic signals as I mentioned previously. So the overall improvements of our project, we met all the city's objectives that they wanted us to clear. We also improved traffic and we improved traffic conditions and pedestrian safety in the area. We improved the air quality and reduced the noise impact from the at-grade crossing. And most importantly, we addressed the key issue of congestion by lowering the level of service from F to about a C. Now we have a cost estimate, as we broke it down into very broad categories. As you can see here, the structural steel was our governing material here for our project, and we had a total project cost of about $36 million.